Hello and welcome back. In particular, welcome to section 13.4, where we'll introduce the cross product operation. So with the dot product operation, that was u dot v. The idea was we took two vectors and we combined them in such a way that we ended up with a scalar, and that was u dot v. So vector u, vector v, scalar. This was good for work. Remember, this translated exactly to work done by a force displacing a object. Right? It was just the force done dot the displacement vector. So that was cool. Here we're going to introduce a new kind of product. This is the cross product or vector product of two vectors. And the idea here is we take a vector u, that's a vector, and a vector v, and instead of producing a scalar in maybe a different way than the dot product, instead what we get is we produce another vector. And this looks like u cross v. And this is a vector. So while the dot product was good for computing work, the cross product is going to be really good for computing torque, which is itself a vector. So torque measures the extent to which an object rotates around another object. So imagine screwing in a bolt or something like that, right? I can either screw to the, righty-tighty, which means the bolt is going to go inward and make it tighter, or I can screw the opposite direction, right? Lefty-loosey, loosen up the bolt, which means the bolt is going to come off. Come off of it, it's going to loosen up. So there is a direction to torque, so that means it's a vector, and it's going to turn out that our new operation here, the cross product, will give us exactly the torque vector. Now, before I get into the definition of the cross product, or vector product of two vectors, I want to talk about a little bit of linear algebra, because this is going to make our calculations a lot easier. So we're going to start with matrices. Ooh. So how do matrices work into this? Well, we'll see. So I just want to start here with how do we compute determinants of matrices. So we're going to need to get, because we're going to be working in 3 dimensions, we're going to need to get a 3x3. We're going to be working with 3x3 matrices and computing determinants of these. However, in order to do this, we first need to understand how to take determinants of 2x2 matrices. So determinant of a matrix, if you are completely unfamiliar with a determinant of a matrix, it's a way to take a matrix and produce a number out of it. I'll keep it as simple as that. I won't go into the linear algebra sort of interpretation of what the determinant actually is. It just takes a matrix and produces a number from it. To do this, to find the determinant of a 2x2, it's easy enough to you multiply these two together and subtract the product of those two. So the determinant of this 2x2 matrix is 3 times 5 minus 0 times -2. So the determinant of this matrix is 15. All right, so again, take a matrix, output a number. When it's 2x2, it's always this. Multiply the diagonal and then subtract the product of the opposite diagonal, I guess. So in general, the determinant of a 2x2 matrix is AD minus BC. Okay, so let's move up to 3x3 matrices. Well, we can actually use the determinant of 2x2s to recover the determinant of a 3x3. So it's not just the same as multiplying all the diagonals and subtracting it from this diagonal. It doesn't work out that nicely. That's not what the determinant is. Instead, what one can do is use something called cofactor expansion. So the idea is I can expand along any row or along any column. I'm going to just expand along the first row here, and then I'll talk about how you can generalize this and actually simplify calculations later on. So I'm going to look along this row. So I'm going to expand along row 1. And what I'm going to do is I'm going to take each of the elements of row 1. So I have a 2, I have a 4, and I have a -1. And so taking a look at the 2, first. What I'm going to do is I'm going to cross off the row that the 2 goes with and the column that the 2 goes with. And I cross those off, and what I have is a cofactor. I have a smaller 2 by 2 matrix, 3, 0, 1, 5. And so I'm going to say the determinant then, so the other notation for a determinant, so I can either write it, I should have done this up here, I can either write a determinant as det of a matrix, or, yeah, I should have mentioned it here, or I can use just vertical bars around the entries of the matrix. That's also the determinant. That's 2 different notations for determinant. And so here, so I took that 2 that was right here, I crossed off row 1, column 1, because 2 was at row 1, column 1. I'm left with this smaller matrix, and I'm going to find the determinant of that. Same thing with the 4, so let me erase this. So now the 4 is it's row 1, column 2. So I'm going to erase row 1 and erase column 2. And again, I have now a 2 by 2 matrix that's left over. 7, 0, negative 2, 5. 2 by 2 matrix. Now I'm going to do something special here. So this first one, this 2 was row 1, column 1. So row 1, column 1. 1 plus 1 is 2, which is even. And what that means is this first one is going to be positive. 2 times this. This is positive. For this next one, I'm at row 2, column, oh, sorry, no, this is still row 1. Row 1, column 2, 1 plus 2 is 3. That's odd. And so this term here, the 4 at the row 1, column 2, this is going to be a negative. I'm going to subtract it off. Right, so let's move on to the last entry of the row. That's the negative 1. That's row 1. So now I'm looking at row 1, column 3. So I'm going to erase column 3, erase row 1. So that's row 1, column 3. 1 plus 3 is 4, which is even. So that means I'm going to add this. Negative 1 times the determinant of what's left over, 7, 3, negative 2, 1. So that is how you do a cofactor expansion. Now you can expand along, what was this? This was a 5, 7, 3. This was a 3. That was expanding along row 1, and we get this expansion. You could also expand along row 2, but keep in mind this thing I did with row 1, column 1, and I figured out if it was even or odd when I added those together. That's going to change the signs, the coefficients on each one of these. Right here it went positive, negative, positive, or plus, minus, plus. If I expand along row 2, I'm going to start with row 2, column 1. 2 plus 1 is 3. That's odd. My first term here would be negative. Then it would go plus, and then minus for the last one. So if you expand along different rows, you have to keep this in mind. Hopefully, a lot of people are also enrolled in a linear algebra class along with this one, and so you should be learning that there as well. If not, it's okay. You can always come talk to me if you need a little bit more explanation for cofactors expansions. But now I have this expanded. Now I just need to compute these determinants of these 2 by 2s. So here, 3, 0, 1, 5, the determinant of that is 15 times 2, so that's a 30 there. The determinant of 7, 0, negative 2, 5, 7 times 5 is 35, minus 0, so that's 35 times 4, that's 120, that's 140, and I'm subtracting that off. Let me do that calculation again. 7 times 5 is 35, minus 0, so 35 is this determinant, times 4, 120. 20, 140. Good. And then the last one, here I have 7 times 1, 7 minus negative 2 times 3, that's negative 6. So that's 7 minus negative 6, 7 plus 6, that's 13. But this was a negative 1 here, so that's minus 13. 30 minus 140, that's negative 110. So this is minus 123 is the determinant of this 3 by 3. for that is what we just calculated. The determinant of this 3 by 3 matrix using cofactor expansion. In general, here's a formula you can use. This is expanding again along the first row. You don't have to expand along the first row. You could also expand along columns or along a different row, but you gotta be careful about the signs here. Plus, minus, plus. Could also be minus, plus, minus. At any rate, this is how you can compute the determinant of a 3 by 3 matrix. This will be very helpful in computing the cross product of two vectors. We'll get more into that later. I'll see you there.